Hello and welcome to our discussion on predicting products. We're going to be focused on our alkyl halides today, so our halogen leaving groups, but this prediction of products is just a really good overview. No matter what reaction we are doing, we should be able to follow this three-step analysis. The first thing we're going to do is we're going to determine the function of the reagent. We're going to look at not only the substrate, the starting material, the alkyl halide, if you will, but we will also look at what's over the reaction arrow, both the thing written to the left of the arrow and anything on top of the arrow we can think of as our reactants. So we want to look at both of those things and be able to describe what function they do. Are they strong? Are they weak? Are they big? Are they small? Are they very substituted or not substituted? Then we're going to analyze those two together and determine the expected mechanism or mechanisms. Now, there could be one mechanism, there could be two mechanisms. We have to be able to think about all four of these, SN1, E1, SN2, E2, and analyze which one or which ones are going to occur. And then we'll consider all of the relevant regiochemical and stereochemical requirements. Remember, regio selectivity is for our elimination reactions. Stereo selection is in a lot of our different outcomes, right? Mainly elimination, but again, when we think about carbocation rearrangements, the SN1 can also have some regio and chemical predictions or requirements to do. So functions of the reagents. I think what I want to do is start off with our bases versus our nucleophiles. I think this is one of the hardest ones. We can look at the function of the starting material and think, is it a primary, secondary, tertiary? What type of alkyl halide is it? This area of base versus nucleophile, I think, is the most tricky to undergo. So I really like this following chart right here. To really help us organize our thoughts. A strong base, but a weak nucleophile, these things that only like to do E2 reactions. H minus 1, when it is, why it's a strong base is because when we think about, I'll just write it up here, H minus 1 going to react as a base with a generic acid, the proton transfer that occurs generates H2 gas, an A minus. Remember what Le Chatelier says, when a gas is formed in a reaction, it bubbles out of solution. And that drives the equilibrium forward. It drives it to make it more products. So H minus 1 is not good at being a nucleophile. It's very good at being a base. And the reason why it's not a good nucleophile is because it doesn't form H2 gas when it goes to be a nucleophile. So it would readily pick up a proton to form H2 gas rather than attack an electrophile and just become a new hydrogen covalent bond with some other atom. It wants to make that H2 gas. Every time it does a proton transfer, that product bubbles out of solution, and so it drives that reaction forward. DBN and DBU are our huge nitrogen bases. These both have a nitrogen with a lone pair. Another common nitrogen one that we've seen before is triethylamine, right? Or diisopropyl, diisopropylamine. Nitrogen is a great base. Nitrogen will not substitute. It's a weak nucleophile primarily because we put such big carbon groups on it. However, nitrogen is a great base because it's so electropositive. It doesn't like to keep that lone pair, and it is relatively stable with a positive charge as a conjugate acid. The last one I wanted to bring up here, which we have seen a lot of, is our oxygens with minus charges. The larger the R group on that oxygen, the weaker the nucleophile, right? So tert-butoxide I threw in here as well, just so that we can see that larger group does become a weak nucleophile, but it still is a strong base. So all of these in that first box on the left are E2 reagents. They are things that would promote basicity, but they'd be too large or unreactive as a nucleophile. The things that can compete and do SN2 and E2 are our strong bases and strong nucleophiles. These are the oxygens with a minus charge that are small, these three. These are the ones that you'll see. Just competing between SN1 and SN2, we have our weak bases and strong nucleophiles. These are things that would not be considered good at doing a proton transfer, but they're fine at being small enough and having a negative charge or having some lone pairs to be able to react. We can see these primarily doing SN2s, or we can also see these being our nucleophiles for SN1s. They're strong because they're small, and they're strong because they're polarizable. Their atom that holds the negative charge is large enough to start to think about shifting some electron density around. And so seeing those guys, we will primarily use these for the weak base strong nucleophile of the SN2. But if you threw one of these in with a polar protic solvent, you can still do an SN1 reaction. It's just a little bit trickier. Primarily what we want to think about with our SN1s and our E1s is this idea of weak base, weak nucleophile. These are the best for the SN1 and for the E1. They're small enough, they're polar protic solvents, therefore these ones would promote the SN1 and the E1. So let's go ahead and dive into a couple of practice problems. Again, let's analyze what we have. We have a secondary alkyl halide. It does have stereochemistry. If we were to do the stereochemistry, 1, 2, 3, 4 is in the back. There's 4. So this is an S alkyl halide. Secondary alkyl halides can technically undergo any of our reactions. So identifying that secondary alkyl halide doesn't help us really determine what we're doing. It just gives us some notes, again, to consider stereochemical or regioselective ideas. Now, when we look at what is over the reaction arrow, we see it's methanol. That is a polar protic solvent, right? So that we want to think about stabilizes carbocations. It is a weak nucleophile. So it's small enough that it can do an SN1 reaction and an E1 reaction. So that secondary alkyl halide tells us it can do anything. What's over the reaction arrow says it's going to primarily promote our carbocation intermediates. So when we're looking at what we want to think about, we want to draw all the products for these. That's where we're going to start to really dive into understanding the products overall, right? And so looking at this, let's go ahead and think about the products. All right, I like to start off with my SN1 first. But again, when we're doing a mechanism for SN1 versus E1, that first rate determining step is forming the carbocation. So both of them would start here, and then we can take it to the substitution and the elimination outside of that. So we'll do substitution up here. Notice that when that carbocation forms, this reaction would be really, really slow. Secondary alkyl halides are not great at making carbocations, but I do think it's an important analysis to take it through to see that when that nucleophilic attack happens, we actually lost the stereochemistry. And even though we still have a chiral center here, what's important to note is that we will get a racemic mixture. Why are we getting a racemic mixture? Well, think about that carbocation intermediate. When we imagine the carbocation, It's got a top and a bottom side. It's trigonal planar, right? So when that nucleophile wants to attack, it can do so from the top or from the bottom. So we are getting a 50-50 racemic mixture where that nucleophile could attack from the top and create one stereoisomer, or it could attack from the bottom and create the other stereoisomer. And then we would just need to do our cleanup step. I'm going to draw out the two stereoisomer products where oxygen attacked from the top and the other, the enantiomer, where oxygen attacked from the bottom. This idea of the nucleophile attacking from the top or the bottom is one of the reasons why an SN1 reaction is not stereoselective. It's not going to select one stereoisomer over the other. It will make both. That's why I call it the Oprah reaction. You get to attack from the top, you can attack from the bottom, you get to decide where you go. Everybody wins on that one, okay? Same thing with our E2 or E1, excuse me, our E1 reaction here. When we think about this alpha, there are options for beta, beta 1, beta 2. Both of them have protons. I'll hang one off here. We'll do beta 1 first. Does not need to be anti-periplanar. Why? Because again, the nucleophile attacked from the top or the bottom for the SN1. The base can pick off the proton, whether it's anti-periplanar on the top or the bottom. There is no anti-periplanar anymore because the leaving group already left. So when we think about all of our options, there's beta 1, alpha to beta 1. I'm going to redraw. Let's just move some of these down for us. I'm going to redraw alpha with the carbocation, beta 2 with the hydrogen, put both of them on there. But again, it doesn't matter which one you pick off anymore. Now, if you find that you get an alkene with stereochemistry in elimination, there's the trans. You automatically know, because this is a carbocation intermediate and carbocations have two sides, a top and a bottom, it's an empty p orbital, you will always make cis and trans, no matter how many hydrogens you have, right? Oprah, you get to be a double bond, you get to be a double bond, you get to be one. So every variation, right? These two reactions, SN1 and E1, are not stereoselective. They are not regioselective. Everybody's going to get informed. All chiral centers, all stereoisomers for our alkenes. Excellent. So 1, 2, 3, 4, 5. 5 different products. We're going to assume that they are going to be equal. I won't ever ask you for major versus minor in SN1 and E1. We'll only do major and minor for our SN2 and E2 reactions. Moving on, I got a couple of reactions for us to do. That one was definitely more complex and definitely a lot to deal with. Let's keep going though. Reaction number 2. We have a primary allylic or benzylic, right? The benzene ring provides a huge amount of resonance, but as we'll see for this, that primary could undergo an SN2 or it could undergo an SN1, right? Primaries don't have a lot of steric hindrance because this is primary with the allylic nature with a pi bond adjacent. We could also imagine that that could form a stable carbocation. So looking at our reagent over the reaction arrow, our base, this is a weak nucleophile. So it can either do SN1 or E1. Let's look real close at our alpha right here and our beta, right? With a primary alpha carbon, we have one beta, and we notice that that beta has two things against it. Not only does that beta have no hydrogen, it's also sp2 hybridized. So we cannot, with this specific example, undergo an elimination 1 reaction. So we will only do the SN1. We'll have our loss of a leaving group. That's where we can see that there is resonance stabilizing this primary carbocation. It's primary benzylic. But again, when we think about the resonance, there's something very special with benzene, and I want to draw it, but we're going to erase it right after that. Benzene can do resonance. It's very helpful for benzene to do this resonance for that position so that we see that that primary carbocation is stabilized. But notice how now one of the double bonds is outside of the 6-membered ring. Just as a general rule of thumb, we would never take this to go make a product. H2O is not going to do a nucleophilic attack here. That doesn't happen. And the reason why is because there's something very stable with the 6-membered ring and all of those alternating pi bonds. Yes, it provides stability, but it will never provide a product. So unlike the allylic position, when we did see back and forth ideas of resonance, we won't ever see resonance coming from this benzene ring that produces a product. We know there's resonance to stabilize the overall charge. However, none of those with the 3 pi bonds outside of the ring will ever form a product. It's something that we're going to learn in second semester with aromaticity. We'll just assume right now benzene's going to stay put as a 6-membered ring. So we do our nucleophilic attack. Make sure you don't drop a carbon there. Right? Keep that alpha carbon where it was. And then we'll follow it up with that little water workup to clean up, to get our one product. That primary is not a stereoisomer, so there's no racemic mixture. It's just the straight one product for substitution. Beautiful. All right, moving right along. Primary alkyl halide. There's no resonance, there's no adjacent pi bond, so this guy can only do an SN2 or an E2. We see our reactive or good nucleophile. It's small enough that we can think about OCH3, methoxide, both substituting and eliminating. Now with a primary alkyl halide, we favor SN2. We can also do an E2. Now we can start seeing, because we're in our bimolecular reactions, major versus minor. E2 will be minor because the primary alkyl halide doesn't have a lot of steric hindrance around the alpha center. When we see E2 is favored, it's because we're in the secondary alkyl halide realm, all right? So we'll start with our SN2, nuke attack, followed by loss of leaving group. We make an ether. I'll redraw. Scroll down. We'll redraw that same alkyl halide to analyze for the E2. Alpha, beta, there's the hydrogen. We know that the backside attack occurs for the SN2, but there's no stereochemistry. A primary alkyl halide we don't often have to worry about with the backside attack being shown or the anti-periplanar, because we know that primary does not have any R or S stereochemistry. So 1, 2 products for this green reaction. Let's scoot things down. All right, let's do it again. We have a secondary alkyl halide. We have a large base that is weak. Take a pause on the video. Try to predict it. What do you think is going to happen? We should see an E1 reaction only. We'll be favoring the Hoffman, but again, E1, we're going to write both, right? We won't be doing major or minor with E1, so I want to see both the Hoffman and the Zaitsev products. Loss of leaving group. I look at that carbocation and I try to think, is there anything that can stabilize it? Next door, there's the ability of a hydride shift. We didn't have that on the first one because when we were thinking about that first reaction, there wasn't anything to stabilize. I'm going to draw in that hydrogen just so that we can see it. But again, it's something that you would not need to draw if you really didn't want to, right? You could erase this hydrogen. I'm only drawing it to show you that that's where that hydrogen went, right? Why I did that is because next door, I'll pop it back on, next door was a tertiary, right? That is much more stable than a secondary carbocation, and we cannot stop hydride shifts or methyl shifts. They are going to happen, and now this is our alpha carbon. So if this is our alpha, beta, I'll call this beta 1. It is the same as beta 1 over here, so you don't have to analyze that guy, but it is the same. There's symmetry here, but there is a beta 2 here with a hydrogen. So let's just quickly identify double bond up there or double bond right there. 2 products. Excellent. Last one that we want to go through is the secondary alkyl halide right here, right? We have a reactive nuke. Again, notice that polar aprotic solvent. I've been trying to throw them on there so that we get used to seeing them. That aprotic solvent acetonitrile is there. So here is where we can do an SN2 or an E2. The major is going to be our E2 because of the secondary nature of that alkyl halide. So again, I still like to do substitution first. I think it's a little bit more straightforward. So I'll go ahead and do that first, just noting that this is a minor product. The substitution needs to show the backside attack, right? We have stereochemistry. So there's one product from that SN2 reaction, and there will always be one product from SN2 reactions. There's a specific outcome. Backside attack needs to be shown. For our E, let's just go ahead and give some room here. For our E2, again, it's a secondary. So what we want to be able to think about is there should be 2 beta carbons that I can choose from. Beta 1, beta 2, however you want to number them. Because that reactive nucleophile was small, again, the major product, specifically now from the E2, should be the Zaitsev, would be major. We still will analyze the Hoffman, but we want to keep Zaitsev as the major. So beta 1, that's the more substituted center. We have 2 hydrogens. Right now, the wedged is the one that is in the anti position. Antiperiplanar. So there's our major Zaitsev product, trans. When we rotate the hydrogen on the dash on beta 1, we will also get the cis. And if we decided to do the mechanism for beta 2, we see we get a monosubstituted terminal alkene. No cis or trans on that one, but this would be alpha and beta 1. Alpha and beta 1 rotated, right? Because there's 2 protons there, so we need to analyze both protons. And then alpha and beta 2. Out of all 4 of these products, let's just move them up here. Major is the trans. Trans is always favored over cis because of steric hindrance with the cis. Minors would be all of the other ones. So analyzing that substrate, what's really important to note is when things are more favored than others, what we will pretty much see is that primaries will have major for the SN2 when you have that strong base and the strong nucleophile, those oxygens with the minus charges. If you have a secondary, it will favor E2 over the SN2. Everything else is pretty much structured when we start thinking about having a strong base or a strong nucleophile. So take the time to really analyze everything on the substrate to help you know which mechanism will dominate. Notice over here on our SN1 and E1s, that idea that we will definitely see them equal, 50-50. I won't ask you who's major or who's minor in SN1 and E1. Okay, let's dive into some other substrates that can do our SN2, SN1, E1, and E2 reactions. These are other good leaving groups. One class that we're going to look at is called the alkyl sulfonates. We talked about this at the very beginning of our Chapter 7 discussion when we were talking about other good leaving groups other than the halogens. Why the sulfonates are good at leaving is because of the resonance that they have when that group leaves. So imagine that we can just think about that leaving group. The oxygen here with the minus charge is quite different than an oxygen, say, for an alcohol, because it's bonded to a sulfur that has other pi bonds. There are tons of resonance structures. We can think about the one going up to the top. We can think about this one down at the bottom. There are tons of resonance structures that the sulfonates can do that help stabilize. Looking at the different types of sulfonates we have mesylate, where that CH3 group is on there. The tosylate, which we will talk about, is more common with this benzene ring with the methyl on it. Common name for that is toluene, so tosylates come from that word. And then the triflate, which is the CF3 group, trifluoro group. They can be abbreviated. You can see their abbreviations NS, TS, and TF on that oxygen group. So these are excellent leaving groups. They're also really large, so we don't tend to draw them all out. We tend to just use their abbreviations. So with these, we can actually think about them being the same as an alkyl halide. You could see them being on a primary alpha carbon, and when paired with a strong reactive nucleophile, we can do the SN2 reaction, which we see here as the major. We can also do the E2, which would be the minor for that primary. For secondaries, remember when we have a secondary, the major product is the elimination reaction when paired with a really reactive nucleophile and base. So we have our E2 mechanism as our major product. Minor is the SN2 for that one. Again, remember the competition between our primary and our secondary alpha carbons. So now we can see that those tosylate groups or any of the sulfonates are really good leaving groups and can be treated the exact same as our alkyl halide leaving group was. So let's just think about how do we actually make the alkyl sulfonate. So we start with tosyl chloride, TSCl, molecule right here over on the side. But again, we like to abbreviate. So in this mechanism, what's really important to note is that we can actually abbreviate TSCl when we do these curved arrows. When we attack that TS group and kick off the chlorine, we are attacking the sulfur group and kicking off the chlorine leaving group on that group, on that sulfur, so that we can create a more stable leaving group. Alcohols, OH, is a very, very poor leaving group. So we get the TS group on there. Now, with the proton on the oxygen, that is not a good leaving group. Imagine that popping up and what you're actually getting is an OH on that sulfur. That looks like H2SO4, so it will not happen that way. So be sure to include PY, usually written on the bottom of the arrow. It's pyridine. That is simply a base. That base is there to deprotonate our oxygen, to make sure that our oxygen can be a better leaving group, to be the tosylate group. OTS. We get a protonated pyridine as a conjugate acid. You do not need to draw that. I just wanted to draw the both the product and the conjugate acid of that final acid base step. So we have a nuke attack with a loss of leaving group, followed by step number 3 overall here, or curved arrow pattern number 3, proton transfer. That proton transfer is important to actually get the OTS group on there. And just to draw it out, O with the sulfur and pi bonds. TS is the tosylate group, so it has a benzene ring with a methyl on the exact opposite side. Alcohols are really bad at leaving groups. They can be used for substitution and elimination, but not in the same way that we saw alkyl halides. We can make that alcohol into a tosylate group, like we just saw, and that therefore can then undergo any of our substitution or eliminations we saw before in chapter 7, or we can do a different type of substitution and elimination reaction. One, not with a nucleophile or a base, but what do we see over the reaction arrow? An acid. Big difference here. When alcohols are the leaving group, OH-1 is reactive, so therefore it is not a good leaving group. So what we have to do is make oxygen a good leaving group. One way is to make it a tosylate. The second way is to protonate it with an acid. So we need a strongly acidic conditions to do this reaction so that H2O is the leaving group, not OH-1. So what you see in that first step is a proton transfer, followed by your SN2 nuke attack, and loss of leaving group. Now, what's important to note is that a primary alcohol, what we have here, alpha carbon that is a primary, will undergo this reaction with SN2 conditions. If you have a secondary or a tertiary, you will undergo SN1 conditions. Carbocation intermediate, loss of leaving group happens first, and then you will have your nuke attack. So again, SN2 conditions, we can make our primary alcohol into a primary alkyl halide via our SN2 reaction. We can do this reaction as well with our secondary and our tertiaries just making note that this is going to undergo a proton transfer and then a loss of a leaving group. We will not have the backside attack occur here before the leaving group has left. So loss of leaving group and then nuke attack, right? SN1 conditions. Alcohols can also undergo elimination. We will use, again, strongly acidic conditions. This will get our alcohol to be a better leaving group. H2O is a much better leaving group. So here, starting with an example that is a tertiary alcohol, we see that tertiaries, just like our secondaries, undergo E1 reactions. We'll have that first step of a proton transfer, followed by step number 2, that loss of leaving group, and then the proton transfer to complete the E1 mechanism. These are great reactions to undergo similar elimination and substitutions with alcohol leaving groups. But again, remember, you have to do something different than our alkyl halides for alcohols. Alcohols are not good leaving groups. So either change that alcohol to a tosylate or use acidic conditions. Let's just again see for our primary, when we think about that water, I'm going to hang off one of the protons on H2SO4 so that I can see that we first do that proton transfer to make oxygen a better leaving group. And then we'll do our E2 proton transfer with our loss of a leaving group to complete our E2 mechanism. This only occurs with primary alcohols. Again, with our tertiaries or our secondaries, we first do our proton transfer, make oxygen a good leaving group, and then we will do our loss of a leaving group, make the carbocation, and then we will finish up with our final step of proton transfer, E1 for our tertiary and our secondary alcohols. So just to recap, for alcohols, you have one of two options. Make them tosylates. And then you can use any of our chapter 7, SN2, E2, SN1, E1 reactions. So this will work for primary, secondary, or tertiary tosylates as according to our primary, secondary, or tertiary alkyl halides. The other option is to use acidic conditions. If we do that, things like HBr, a primary alcohol, will undergo SN2, a secondary or a tertiary alcohol will undergo SN1. No way around that. Carbocation rearrangements will occur if possible. With H2SO4, a primary alcohol will undergo an E2 reaction. With H2SO4 and a secondary or a tertiary alcohol, will undergo SN1. No way around that. Carbocation rearrangements will occur if possible. With H2SO4, a primary alcohol will undergo an E2 reaction. With H2SO4 and a secondary or a tertiary alcohol, will undergo SN2. we will undergo an E1. Again, carbocation rearrangements, all products available.